We now look to a multiple writer, multiple reader algorithm that is sequentially consistent. So we are going to show an algorithm. We call it LT for obvious reasons that will be clear right now. It is an algorithm in the fail-silent model that implements read-write multiple register shared memory. So we have multiple writers and multiple readers. It is sequentially consistent. So executions are sequentially consistent of this algorithm. And it implements write operations in one round trip and read operation in two round trips. So compared to the linearizable registers, which requires two round trip for writes. And the reads is as usual, two round trips, but sometimes it can take one round trip if there's no overlapping writes with the reader. And it tolerates up to less than half of the processes failing. And we call this algorithm LT because we are going to use logical time in this algorithm. So as we know, unlike linearizability, sequential consistency is not a compositional consistency condition, but the algorithm that we are going to present, called LT algorithm, the logical time algorithm, satisfies the sequential consistency conditions, but also satisfies a bit stronger consistency condition that is compositional. And we use compositionality to prove that the algorithm works fine for multiple registers. So we'll have a simple proof, and we get scalability, allowing storing subsets of different registers in different replication groups on different sets of processes, and therefore we can scale up the whole system. The LT algorithm linearizes reads and writes in logical time instead of real time. And executions, which are real-time traces, are sequentially consistent instead of linearizable. So we have linearizability in logical time, which allows compositionality, and we're going to use compositionality. So the LT algorithm will satisfy sequential consistency, but it will also satisfy a bit stronger consistency condition that is compositional. We will see that later, what are the extra constraints that this algorithm have compared to sequential consistency. So now let us look to the algorithm, and first of all I have to remind you of logical time and clocks. So we have the happen before relation between events. So this notation says event E precedes event E prime, and this can happen if E occurs before E prime on the same process, and E is the sending of a message M, and E prime is the delivery of that message. And the relation is transitive. We have seen that before. And if just to remind you of the property of logical clocks. So logical clocks assigns to each event a logical time. We call it LT. And this logical time is such that if an event E precedes another event E prime, then the logical time for E is less than the logical time for E prime. So the algorithm that we are going to show implements a logical clock per process as an integer variable named LT that is updated at the beginning of every computation step as follows. If we do a local computation step, then at the beginning of that, the clock is incremented. If we do a send operation M, we include the current logical time in the message. And if we receive a message M, we update our clock to the max of the local logical time and the logical time in the message, and then we increment that by 1. So each process stores all values of all registers, and a typical register value, as we have seen before, is a timestamp value pair of this form. And TS determines which value is more recent. And what is the timestamp? The timestamp will be a logical time and process identifier, so it's a pair of this form. Here is the logical time, and here is the process identifier for process PI. And each process stores all registers, and every register is actually the timestamp value pair and the value of the register initially undefined. Now we have the write operation. It only uses an update phase. It doesn't use a query phase. So how does it work? So to write register R, the value V. So PI forms the pair with its own logical time and its own process ID and the value V, and we said that LT is a logical time. PI starts an update phase by sending an update request with the register and the timestamp value pair TP. All processes, for example PJ, update the value of the register to the maximum value of the local register and the timestamp value pair that it has received and response. And PI completes the write when the update phase ends. To do a read, we are going to use two phases, a query phase and then an update phase. So to read the register R, process PI starts a query phase and it sends a request with the register identifier R. Every process, in this case for example PJ, responds to the query with its current timestamp value pair for register XR, and when the query phase ends, PI picks the maximum timestamp value pair received. Then PI does an update phase with that timestamp value pair that we just talked about and register XR. So after the update phase ends, PI returns the value V, and we have seen this before. So let us look now to one example execution which is sequentially consistent. And we have three operations. These are the operations that we have. A write, register X1, we are going to use only one register with the value 5. A write of register X1 with the value 6, and here is a read operation of the register. When P1 starts the write operation, it does an update phase, and in the update phase the timestamp value pair has a logical time 10. So when the write is complete, the value 5 will be associated with the timestamp 10. Then P3 in real time starts another write operation, but the logical time here is 5, and it completes the operation of writing the value 6. But because the logical time of the previous write, of this write, is higher than the logical time of this write, then the maximum value that will remain at this point will be X1 equal 5, and it has a timestamp 10 and coming from process 1. So when the read operation starts, in the query phase is going to pick up this value, and that is the value that is going to return here. So you can see from this example that this execution is not linearizable because the green write happens after the blue write, but the read reads from the blue write. So we are going to look at the traces of these executions, and here is the trace. We have the invocation event of the write, the blue write, with its response, and the invocation event of the green write with its response, and the invocation event of the read and its response. And this is the real-time execution, the trace T. Now let us look why the executions we get by this algorithm is sequentially consistent. Just let us remember sequentially consistent again. A trace is legal if it is sequential, and each read reads the last value written, and two traces S and H are equivalent if each process has the same view in the two traces. And we said that property is sequentially consistent for some trace or a history T if there exists a legal trace S and the trace is equivalent to the original real-time trace. This was the example we have just shown earlier with the 3 processes. And in this execution, we have a sequentially consistent execution because we can take this write and place it between this read and that write. So place it here. And we get a sequentially consistent execution. So the trace that we have is sequentially consistent for that specific example. Now let us look to the correctness of the logical time algorithm.